Okay, so in this next example, we're evaluating a line integral. It says evaluate the line integral along C of f dot dr, where f is this vector field given here, I plus x plus y zj plus xy minus square root of zk, and C is the boundary of the part of the plane 3xy plus 2y plus z equals 1 in the first octant. The very first thing I'm going to want to do is sketch that part of the plane that's being described there. So it says in the first octant. Let's take a look at what that would look like. Remember, these things tend to look like little triangles in the first octant, and we've determined the vertices of that triangle by finding the intercepts of the x, y, and z intercepts of this plane. So, for example, if I plug in a 0 for x, y, and z, I get 3x equals 1 or x equals 1/3. That's going to be that intercept. Similarly, I'm going to get a 1/2 for y and a 1 for z. So that gives me this guy right here. Okay. Now, I happen to notice that this graph right here looks like the graph of a function. It passes that version of the vertical line test that we can use. So I have a hunch we're going to need the region D down here in the xy plane that would act as that part of the domain of the function, giving me this surface here. So let's go ahead and look at that next. So D looks like a triangle. The y-intercept is 1/2. X-intercept is 1/3. So that's that region D right there. And the graph of this, or the equation giving me this line right here, is going to look like y equals 1/2 minus 3/2 x. Relatively easy to come up with the equation of that line. We're going to need that. Okay, so again, I can evaluate this directly if I want to. If I give, you notice it doesn't indicate what the orientation of C is, but if I were to give C a positive orientation, C, remember, is the boundary of the surface that we're talking about here. C actually says the boundary of the part of the plane 3x plus 2y plus z equals 1 in the first octant. So this guy, right? I would have to evaluate 3 line integrals if I wanted to do that, because this is a piecewise smooth curve, and I'd have to break it up into these 3 pieces, do all 3 line integrals. It's not fun approaching it that way. So we're going to attempt to use Stokes Theorem. Now here's something we haven't mentioned yet, but it's an extremely powerful consequence of Stokes Theorem. If we go back here, this line integral is equal to this surface integral as long as C is the boundary of that surface. What that means is that this surface can be one of infinitely many different surfaces just so long as it has the same boundary. Does that make sense? If you look at problem number 1 in this section, it gives you 2 different surfaces that have the same boundary curve. And it wants you to show that according to Stokes' theorem, a certain integral involving those 2 surfaces is the same. So I can choose, if I'm going the other direction, if I'm being asked to evaluate this line integral, and I want to turn it into a surface integral, I can let this surface be any surface that I want, just so long as it has the correct boundary curve. So generally what we do is we let this surface be the easiest possible surface to work with. What I'm going to do is let that surface just be the plane, this plane here, since I already have an equation for it. Okay, so now in order to do that, let's begin by finding the curl, because I'm gonna need to find the surface integral of the curl of a function here. So what is the curl of f? Remember, curl is a cross product. You can think of it as a cross product of del with f. So it's going to look like this. X y, z, and then my components for f are 1x plus yz, xy minus root z, okay? If you evaluate this, what you end up with is x minus y I minus y k, oh sorry, j, that should be a j, plus k, okay? Now, what we want to do is use Stokes' theorem here, which says that this line integral can actually be evaluated as a surface integral of the curl of f dot ds. So that is this. Line integral of f dot dr, according to Stokes' theorem, is, and this is the surface S up here, this part of the plane, the surface integral over the surface of the curl of f dot ds. Now, I had mentioned previously that this surface S looks like the graph of a function where d is the part of the domain that we would plug in to this equation here to get that surface. Previously, let's see where I wrote that, I had said in the proof of Stokes' theorem, or I had cited a theorem we already showed. If I want to find the surface integral over a surface S that's the result of a, or the graph of a function of f dot ds, then that's the same thing as the double integral over that region D in the plane, the xy plane, of this, negative p partial of z with respect to x, negative q, or minus q partial of z with respect to y, plus r. P, q, and r being the components of that vector field. Well, in this case, the vector field is the curl, and we have the components of the curl right here. What's still needed is the partial of z with respect to x and the partial of z with respect to y. So let's find those. Partial of z with respect to x. Notice in order to do that, I actually need to solve this for z. So I'm going to get z equals 1 minus 3x minus 2y. Partial of z with respect to x would be negative 3. Partial of z with respect to y is going to be negative 2. So I'm going to need those. Okay? Using that formula, we want negative, this becomes the double integral over d of negative p, that's negative this, x minus y, times the dz, or the partial of z with respect to x, that's negative 3, minus my q, my j component here, so minus negative y means that's plus y, times the partial of z with respect to y, which we found to be negative 2 up here. Oops, that was off screen, wasn't it? I think I keep doing that. Plus r, where did that go? Oh, sorry, yeah, I was looking at the wrong thing. So r, which in this case is the k component, the k component is just 1 plus 1 dA. Or, after simplifying things, 3x minus 5y plus 1 dA. Okay? Now, we went through and found a representation for this region D as a type 1 region, which gives me a method for turning this into an iterated integral. This is going to look like, notice x goes from 0 to 1/3 here. 0 to 1/3. And then my y goes from 0, from 0 up to the equation y equals 1/2 minus 3/2 x. So 0, 1/2 minus 3/2 x of 3x minus 5y plus 1 dy dx. Okay. In the interest of time, because this is a relatively straightforward iterated integral with a type 1 region, I'm going to just skip to the answer because we've done several of these up until this point. It's just there's kind of a lot of work to write out, but none of it is difficult. It's just a lot. This comes out to 1/24. Okay? I encourage you, just for practice, to try and get from here to verify. Okay? So that is that. All right. We had a couple of conceptual things that we wanted to talk about to wrap up this section on Stokes Theorem. And one of them is something I alluded to earlier when we introduced divergence and curl. I had said before that the curl of a vector field is sort of a measure of the tendency. So let me say this a little differently. If you take the curl of a vector field at a specific point in that vector field, and in particular, if that vector field is something that, if you think of it as the velocity field of a fluid flow, then the curl at a given point is the tendency of that fluid to rotate around that point, where the curl represents the axis that it would be rotating around. And we use kind of the analogy of if you put like a little paddle wheel on that axis given by the curl, the actual curl itself is going to tell us the tendency of that paddle wheel to rotate either clockwise, counterclockwise, or not at all. Remember, if the curl is equal to 0, we say that it's irrotational. So how do we make sense of that? Well, Stokes' theorem sort of gives us a technique to do this. Now, this is very conceptual. Okay, so this is just to give you a sense of where we even get the name curl from in the first place. So what we're going to do is let V be the velocity field of a fluid flow. So it has a specific interpretation, this vector field V. And C is going to be some positively oriented curve in that fluid flow. Now, the line integral along C, that positively oriented closed curve of f dot dr, which in this case looks like v dot dr, remember, is the same thing as the line integral of C of f dot t ds. V dot t is the component of V in the direction of t. But if we're talking about a simple closed curve C like this, remember t is the unit tangent vector. It basically gives me the direction at any given moment that a particle is traveling along that curve C. Now, I know from our work on dot products that the dot product of V with t becomes larger the closer V is to being in the same direction as t. And in particular, if this angle here is acute, then we have a positive, or V dot t would be positive. If it's obtuse, V dot t would be negative. But because the particle will be more inclined to travel along this, a particle is more inclined to travel along this curve in this fluid flow if the velocity of that fluid flow is in the same direction as t. Then this quantity, this integral along this line integral of v dot t, it gives us the tendency of the fluid to move around that closed curve C. I know that might be a little bit difficult to imagine, but we call this integral the circulation of V around C to give us sort of that intuitive concept a name. All right, now if I let P naught be some point in this fluid, and if I let S of A be a small disk of radius A centered at P naught. So we're in this fluid flow, I have this P naught here, and I want to take a small disk, which I did not draw very well, and call that disk S sub A. The A indicates the radius of that disk. Because the vector field F is continuous, one important way that we understand continuous functions is that small changes in the input of a continuous function correspond to small outputs, or small changes in output, not small outputs. What that means is that if this circle is small enough, if I were to take P naught and evaluate the curl at that point, and then if I pick any other point that's in this disk, that point will be close to P naught, and so the curl of that point should be very close to the curl of P naught, because the curl is continuous. Now again, we didn't assume anywhere that the curl of V is continuous, but V is a continuous function, and we know that because of intuition. A fluid flow, it wouldn't make sense for it to be to not be continuous. The curl of a continuous function will also be continuous, so that as long as it has continuous partial derivatives, all of those things are satisfied. Don't worry over that. That continuity, though, says that the curl of f at p naught is going to be approximately the same as the curl of any other value p contained in that disk. So if we apply Stokes' theorem to this boundary curve, which we're going to call CA, the boundary of that disk SA, then what that says is that the line integral along that boundary curve CA of f dot dr using Stokes' theorem is equal to the surface integral of the disk SA of the curl of v dot ds. Now, this is the same thing, remember when we evaluate these surface integrals, as that surface integral of curl of v dot n ds. And we're specifically using this approximation here because if p is a point that's actually on this curve CA, then this curl, the curl of v is approximately equal to the curl of v at p naught, and the normal vector will be specifically the normal vector of, or is going to be approximately the normal vector at p naught, because again this will be a continuous function as well. The point of going from here to here and using this approximation is that because I'm using a specific point p naught, this whole thing in here becomes a constant. You can bring that constant out of the surface integral, and what's left is the surface integral of over s of a ds. If you remember, the result of that will just be the area of that surface. Now this area would be pi a squared because the surface is a disk of radius a. So this line integral, here's where we use Stokes' theorem, and then we use some approximations that we set up earlier, is approximately equal to the curl of v at the point p naught dotted with the normal vector at p naught times the scalar pi a squared. If I divided both sides of this by pi a squared, I would get 1 over pi a squared times that line integral that we had talked about before is approximately equal to the curl of v at p naught dotted with the normal vector at p naught. I'm saying approximately because we have this approximation right here. However, if you shrink a down towards 0, intuitively that approximation gets better and better. And because p naught, it doesn't look like it here, but p naught is supposed to be the center of that disk. If you let a approach 0, then this disk is shrinking down to that point p naught. And in the limiting case, we get equality. So what this says is that the curl of a vector field at a specific point dotted with the normal vector at that point, or the unit normal at that point, is equal to the limit as a goes to 0 of 1 over pi of a squared times our circulation. This is the circulation. Now, as a goes to 0, yes, this denominator goes to 0, but so does this circulation. So it becomes an indeterminate form, a 0 over 0 type, which those can give us finite limits. So this would exist. This is essentially a scalar here, the 1 over pi anyways. And so this is just a scalar times my circulation. It's a scaled version of my circulation. So using the intuition that we talked about before, this is maximized, this represents this curl of v dotted with the unit normal n. So now this is at a specific point. If I generalize this to any point, I could just say curl of v dot n. It's equal to a scaled version of that circulation about that point. So it represents the rotating effect of my velocity field around the point p naught. And then on top of that, we said that this dot product is going to be maximized if the vector v is aligned with the normal vector n, if they're pointing in the same direction. What that means is that the rotating effect is maximized about the axis parallel to that normal vector. Okay, so that sort of brings a little bit more rigor into that idea that we talked about of the curl representing the axis of rotation of a velocity field about a point. Hopefully that made some kind of sense. Last thing I want to do is wrap up a theorem that we had talked about back in, I want to say it was 16.3, or no, 16.5, I think. Yeah, 16.5, which said that it was the converse, or a partial converse of a theorem we'd already stated. It said if you have a vector field f defined on all of R3, and if the curl of that vector field is equal to 0 on all of R3, then F is a conservative vector field. And when we mentioned that theorem back then, we said we can't prove this yet, but once we get Stokes theorem under our belt, we can prove this one. And with Stokes theorem, the proof is very, very straightforward. So what we do, remember this vector field we're assuming is defined on all of R3, so I can look at any closed path in R3, and I'm going to let S be an orientable surface with that boundary with a boundary that is equal to C. Stokes theorem would say that the line integral of line integral along C of f dot dr would be equal to the surface integral of the curl of f dot ds, but the assumption that we're making is that this curl is equal to 0, right? So that would mean that my surface integral has an integrand of 0, and that would come out to 0. So what does this mean? Well, the line integral of any closed curve of f dot dr is equal to 0. We had a theorem before this one that said that if the line integral of f dot dr along every closed curve in the domain of a function is equal to 0, that would imply that f is conservative. So that gives us the result that we're looking for, because that curve C was chosen arbitrarily. Okay, this stuff is this last page here is conceptual stuff. It's kind of giving meaning to these concepts in a more general way. For you, what's going to be the most important is understanding the two examples that we worked through in this section, actually applying Stokes theorem to the evaluation of either a surface integral or a line integral along a closed curve. But that's it for 16.8.